My name is Leonidas. I'm a postdoc researcher in the University of Argos, working in the telecommunication systems laboratory. And today I'm going to present the Frontend system of the Argos project. Here I have a brief outline. First of all, the work that I'm going to present was carried out by two researchers, Argos and Vasilis, who is here, supervised by Professor Leonidas. And first, I'm going to say a few words about the work packets describing the front-end subsystem. And I'm going to describe a few front-end architectures, a few alternative scenarios that we have investigated together with the Max Planck Institute engineers. And then we're going to spend a few slides on the reflector antenna, on the dish reflector alternatives, on the feeder antenna designs that we are designing in our laboratory, and a few slides talking about the fabrication of the feeder antenna, because we're going to make a custom made, let's say, phone antenna for the feeder of the dish reflector. And we're going to fabricate it in collaboration with the German company. And then I'm going to present a few simulation results from the parabolic dish reflector antenna, and also present some action points for our future work, and of course any questions if you have. So first of all, about the work packets of the Argos project and the front-end subsystem. The objective, of course, of this work package is to design, experimentally validate and document the front-end subsystem of Argos. And in general, when we say front-end, we mean actually the RF part of the receiver, the RF chain, as we usually say, and all the components that we actually use in order to capture the RF signals and transfer them to the digital backend part of the Argos, of course. Components like this reflector, the feeder antenna, noise source for the noise calibration, directional couplers, LNAs, filters, connectors, cables, etc. And this work package, of course, is based on investigation tests and not the optimal integration of this system. And all partners of Argos project participate. We in University of Argos, together with Max Planck Institute, we are the coordinators, and the lead in the investigation are led by Professor Leonidas and Gundolf Winting. These are the tasks of the work package. We are currently in a quite busy, let's say, period. We have finished, we have completed the first two tasks about the market survey and the front-end, let's say, subsystem requirements. And now all the rest of the tasks are have started. They are ongoing. So we are in a quite busy, let's say, period of the front-end work package. Some basic features first. About the architecture, of course, we are talking about a feeder antenna with two polarizations, linear polarization, horizontal and vertical. And we are going to achieve that using a quad-reached flared horn antenna. We want to achieve, of course, a low noise receiver with a wide instantaneous bandwidth. The board that the Max Planck Institute is going to build is going to have two LNAs in series. We are not going to use cryogenic cooling due to battery constraints. And there's also a bandpass filter between these two LNAs in order to eliminate the RFI frequencies, these signals, and reduce the saturation and the modulation to our system. And of course, we also want to apply some noise calibration. We want to inject a noise signal. And in collaboration with the Max Planck Institute, we have investigated a few scenarios about how this noise injection is going to be achieved. a really preliminary idea, a really first scenario was an idea that Christoph from Max Planck had to inject the noise signal to the circular waveguide of the antenna. Have a probe, let's say, at 45 degrees orientation between the two polarization at the circular waveguide part of the antenna and inject the signal there. But we investigated a bit this scenario and we dropped it because we thought that it's quite impossible to have an equal noise power through the whole band because the band is quite big, it's 1 to 3 gigahertz. So we have a quite big variation, like a 10 dB variation at the noise power. So we dropped the scenario. The next front-end architecture scenario that we investigated is by using two directional couplers, 4-arm directional couplers with 50 ohm terminations at the fourth arm, and the power splitter in order to take the noise signal from the noise source and split the noise signals to the two directional couplers. And so this is the next scenario that we investigated. The coupling of the directional couplers is 30 dB. And again, we thought that this may have a problem. And we thought that maybe it's a better idea, and this is the next scenario, to forget about the power splitter. Because this way, so you see the difference actually between these two scenarios is that we don't have the power splitter, and we just feed the noise signal to one bidirectional coupler, the lower one, and then pass it to the upper one. This way, we actually eliminate this power splitter and we don't have the insertion loss. This is quite trivial, of course, for a system like this. Because if we have, let's say, power splitter with just 1 dB or half dB insertion loss, then we can save some Kelvin degrees at the system noise temperature. 1 dB insertion loss provides additional 70 or 75 degrees Kelvin at the system noise temperature. So this is very critical. And at the end, there is a final scenario. It seems that we are going for a solution like this. We're going to have the whole noise, let's say, injection and the coupling on the Max Planck board, actually, embedded on the Max Planck board. So there's going to be a noise coupler, which is going to be embedded at the input matching network of the first LNAs. Yeah, the color is really light, and you cannot see the triangle at the first LNAs anyway. And this is going to save also. It's going to reduce, let's say, the system noise. No need for separate directional couplers, no need for extra cables or like this, things like that. And then, of course, we have the two LNAs and the bandpass filter always at the middle of the two LNAs in order to eliminate the RFI frequencies. So these are a few front-end architecture scenarios that we have investigated. This is the last one, but currently I think we are going for this one. And a few words now about the reflector antenna and the basic features of the reflector antenna of the Argos project. We want to make actually a simple, cost-effective, as John mentioned earlier. There is always, you know, a trade-off between cost and performance. We want to make a simple, cost-effective reflector antenna due to budget constraints. It's going to be a parabolic dish reflector, so we're talking about one reflector, prime focus, axial, front fend, as you can see from the picture. As we said, it's going to be a dual polarized feed horn antenna with a bandwidth from 1 to 3 gigahertz. And the whole receiver, let's say, is going to be a feed box, which is going to be attached to the feeder antenna. So we want everything like and the feeder and the whole receiver all together at the focal point of the parabolic disk, because we don't want any extra cables, of course, introducing losses. And as you can see from the picture, when we're talking about this kind of big dimensions, let's say, of course, we're talking about supporting mechanical structures. We also need some rigid foundations, some cement support structure in order to hold steadily all this heavy structure and withstand the winds and the mechanical torque. And here in this slide, I have some basic specifications about the reflector antenna. Of course, we want as high, the diameter as high as possible. As John mentioned earlier, let's say a spec that we had from the astronomers was to have a diameter of 6 meters, and the F over D ratio is not locked yet. It's actually a discussion point. Maybe so far we have done many simulations using F over D ratio of 0.38. This is employed so far. And we are using actually this because this is a really common value for the F over D ratio in the market. If you want to buy a reflector off the shelf and you want to a custom made, let's say, design for the reflector, and you want to buy a red one off the shelf, then the value is going to be 0.38 or 0.4, something around this. Some other specs of the disc gain, we are aiming for a gain between 33 and 41 dpi. Of course, depending on the frequency. We have a 10 dB taper angle of around 120 degrees. The gain of the feed antenna is around 11 to 14 dpi, again, depending on the frequency. And we definitely want to achieve, of course, very good isolation between the two ports, the horizontal and the vertical polarization, over 40 dBs, of course, and a quite good matching of the antenna, of course, below 15 dB for the reflection coefficient. So we actually performed an extensive, I would say, market survey. We have contacted and spoke to numerous companies that make reflectors in order to see what we can purchase from them and what are the specs. And you can see at least 15 or 20 different brands, let's say, companies that they make reflector antennas. I have in bold letters 3 companies that we think that they are the best, let's say, solutions. So now we narrow down all these choices from just 3 companies: the POM Electronics, the Anti-Sky, and the Megatron. It's a Greek company here based in Crete. And the parabolic disc specs, of course, it's first of all the low cost, because this is something quite important. The budget is not huge in Argos, so we are really aiming for a low-cost solution for the reflector. The disc diameter is locked; it's a 6-meter diameter. The focal ratio so far is 0.38. We want a polar mount with azimuth and elevation scar and motorized control. And there was, at the start, there was also a really strict specification about the special weather conditions, because we had in mind that a really a site location in Skinagas up in the mountain, it's a really good candidate. Let's say we thought that this is the best candidate for the pathfinder. And the guys from the fourth told us that there are really strong winds there and snow for a few months during the year. But now that we have performed during the summer some RFI measurements, it seems that this location now is not the best candidate. So maybe the last spec about the special weather conditions is, let's say, out now. So this is the first alternative, the reflector from the POM Electronics. 6-meter prime focus parabolic mesh reflectors, of course, with feed arms and motorized mount. Transport to grid also in the price, very important for us. It's a mesh reflector, which means that we need a gap when you're using a mesh dish, a mesh reflector. We want the biggest frequency, the greatest frequency that we are using is 3 gigahertz. The mesh gap should be lambda over 10 or something less than that. So we are looking actually for a mesh gap which is smaller than 0.9 centimeters in order to have a good performance at 3 gigahertz. The F over D ratio for this specific dish is 0.40. Elevation range, of course, and azimuth range, full azimuth range, 0 to 360. And again, at around 43 dpi at 4 gigahertz. This is something that they have tested in the company. And this is the second alternative for the reflector. It's a company from China, the Sky. But this doesn't have a motorized mount, it has a manual mount. And the specs, of course, again, operating frequency 1 to 3. Material medium, finished spray plastic, and some specific values about the winds. And this is the third alternative. It's a company based in Crete, Megatron. They are experts actually in motorized solar panels. They are quite recently introduced to these reflectors. But the very good thing, the advantage using this, let's say, choice, is the fact that, first of all, we're talking about a custom-made reflector. It's not off the shelf, so we can change, for example, the F over D ratio, or anyway, we can change the specs. And the second great advantage of this choice is the fact that they are based here in Crete. So the installation of the elements, of the array elements for the Pathfinder and the service, it's going to be, of course, easier, more efficient. Okay, now a few words about the feeder antenna that we are actually designing in our lab. As I mentioned before, we're talking about a quad-reach flare-form antenna. As you can see here in the picture, it's a custom design, dual polarization, with a pair of ridges, as you can see, per polarization. You can see the 4 ridges, and 2 orthogonal monopole probes. If you see the cut plates that I have down the right corner, you can see the 2 monopoles. Of course, they don't really coincide, but they cross each other. They are really in a close distance, but not very close in order to have good isolation. All the simulations that we have done for the feeder antenna, they are performed in CST Microwave Studio. And so far, we have 2 main alternative designs, a straight flare and the bell-shaped flare. The one that you are watching now is the bell-shaped. But let's start with the other one. This is the straight flare. It's a normal, straight, conical, let's say, shape, as you can see. You can see the 3D patterns for the 1 gigahertz and the 3 gigahertz. I took the 2 frequencies at the edge of the frequency range. Here we can see the same pattern, radiation pattern for the 2 polarization at the 2 ports in 2D. You can see that the beam is not perfectly symmetric, let's say. It's a bit squeezed, let's say, as you can see from the cuts, and there are slightly slight differences in the gain. But the side lobe level is quite good. It's minus 16 dB for 1 gigahertz. This is the same pattern, radiation pattern for the 2 gigahertz. Here you can see that the side lobe level is quite weak with this design. And at the 3 gigahertz, it's even worse. You can see that for the 3 gigahertz, this design gives a quite poor disturbed pattern, let's say, and the poor realized gain. and the side of level, it's just minus 8.5 dBs. That's why we then did some trials. And first, before passing to the next one, this is the S parameters of this straight flare-borne antenna. You can see the S11 and the S22 way down minus 15 dB, which is it shows demonstrates a very good matching, and S12 and S21 through the whole bandwidth 1 to 3 gigahertz below the minus 40 dB. It shows a very good isolation. And here you can see also a plot gain versus frequency of the antenna. The gain varies from 11 to 14.5 dBi. But yeah, as I said before, this design didn't have very good patterns and at the higher frequencies at 2.5 and 3 gigahertz. We have quite high side lobes, and this of course affect the overall gain of the feeder antenna. Therefore, we tried another shape. It's a bell shape. It's the same, let's say, type of antenna. It's a quad ridged again. It's flare borne antenna, but now it's not straight. It has a bell shape formation. And you can see the 3D radiation patterns for 1 and 3 gigahertz. And here you can see the difference. You can see that the two cuts are more similar, let's say. It's more symmetric, the beam, the radiation beam of the antenna. And the side level, as we go up, it's really good. It goes down to minus 21 and minus 25. So this was a really very good improvement that we achieved with this type of design. This is the S11 again. We can see we are below minus 14, minus 15 dB for the matching, and very, very good isolation below minus 60 dB for the isolation between the two ports. And here you can see again the gain versus frequency. It's a bit more flat than the previous one, the previous design, achieving a gain from 12 around to 14 dBi. And a few words about the fabrication, because we designed this antenna and we want to fabricate it. We will fabricate it in collaboration with a company based in Germany. It's called Golden Devices. I have put a couple of pictures of some designs that we have fabricated recently. We also have some experience in 3D printing horn antennas and metallization. We have done this at the past. We have done some horn antennas at 10 gigahertz. But now we will collaborate with this company in order actually, this is actually the process, the whole process of the fabrication. We're going to do, of course, the simulation, the optimization of the simulation. Then we're going to perform the additive manufacturing and the metallization. And of course, this gives three main advantages. The 3D printing and the metallization compared to the normal CNC machining, let's say, if you want to make straight from metal your horn antenna. And instead, if you do it from plastics, let's say, with 3D printing, and then you metallize it, you coat with nickel or gold or copper your structure. This gives you three main advantages. The first one is the lightweight structure. Of course, it's the reduced. The second one is the reduced production time, and it's the third one is of course the cost, which is quite critical for us. And these are the exact steps actually that we are going to follow in order to achieve this fabrication using the 3D printing and the metallization. First, we're going to actually follow a split block approach. We're going to divide, let's say, the model in 4 or 5 parts and print separately these parts. We're going to use SLS, selective laser sintering 3D printing, and the coating is going to be with nickel. And of course, we're going to have some experimental verification afterwards. The estimated weight is going to be 3 to 4 kilograms, which is quite impressive. If you imagine that we're talking for a horn antenna that is like 50 centimeters by 50, it's that big. So 3 kilograms for a structure like this, it's quite a good point. And because we're talking about an outdoor installation of the antenna, we need some kind of protection from the rain or from anyway from the weather conditions. So we're going to use a special plastic front cover at the front of the horn antenna, made by a special material FDM. It's called SAA with these characteristics, this material is tested at the past. We know it's, let's say, electromagnetically transparent. It doesn't disturb the radiation pattern of the antenna a lot. And here I have some slides talking about the simulations that we did. You know, we finished. Let's say we have completed the design of the feeder antenna. So now we did some simulations in CST using also the reflector disc, the 6-meter diameter disc, and the feeder. Altogether, we actually followed the SAM system assembly modeling approach by CST. It's a bidirectional coupling approach, which means that the full geometry model is used, disc and feed. So we're talking about all losses. They are actually considered in these results, like spillover losses, illumination losses, blockage losses, matching dielectric losses. And here we have some results. This is the S parameters. Again, we are for a quite good portion of the frequency band, 1 to 3 gigahertz. We are below minus 14 dB, so we have a quite good impedance matching for our dish reflector antenna. And here you can see the 3D patterns of the whole structure. Of course, we're talking now about gains around 30, 35 or 40 degrees as we increase the frequency. And here you can see the 3 different radiation patterns at its 1, 2, and 3 gigahertz. We achieve again around 39.4 or 1.5 dpi. And this is a plot for the gain versus frequency. And at the end, we also did the spillover efficiency investigation in order to calculate the spillover. We actually calculated the power flow inside this volume and the power flow over the whole spherical space, and we calculated the spillover efficiency. It's the blue line that you can see in this plot. And at the end, some action points for our future work. We are planning to do a 1 or 2 days meeting in fall. I don't know, in December. With the Max Planck Institute, we're going to go there in order to discuss about the interface between all the antenna parts that we are doing in the University of Piraeus and the Max Planck board and the rest of the RF chain and the front-end system, let's say, how we're going to interface. Of course, we're going to adjust our system designs and optimize the feeder design, place the order for a feeder fabrication, and place the order also for the parabolic reflector. And at the end, of course, we are planning to do some experimental verification. The feeder that I demonstrated today is going to be measured. The pattern is going to be measured in an anechoic chamber. And the reflector of this antenna, the parabolic reflector antenna, again, the pattern, we are willing to measure it. But of course, this cannot be done in an anechoic chamber because the far field of a huge antenna like this is something like 600 meters, I think. I calculated it, something like this. So in order to measure the pattern of a huge disc, you have to follow some more tricky ways, and we are planning to do that using a drone. We recently purchased a huge UAV drone that can carry some lightweight RF equipment, measurement equipment, and some antennas, and we are willing to do a pattern measurement on the field, actually. And that's for me. Thank you for your attention.
Thank you, Leonidas. Any questions?
Do you have the shell antenna that you showed? What is their lifespan typically? How often do you think they will need to be replaced or maintained in any way?
Yeah, this is something that we haven't really discussed in detail with these companies. I believe most of them are made by steel material. I think it's definitely more than let's say 10 or 15 years, but yeah, I don't know if Vasilis who have made some
Well, it
contacts.
actually depends on the weather conditions that the antennas are. For example, if they are not going to be in a place where there is a lot of humidity or like snow, they will last much longer. But I believe like 10 years will be
Okay.
Yeah, that was a quite critical issue when we were discussing the fabrication of the feeder, for example, the copper coating, because you can metalize your 3D printed structure, the horn antenna, you can metalize it with many ways, like with gold, with copper, with nickel.
For gold, the lifetime would be what?
Yeah, the best one electromagnetically, let's say, wise, is the copper. But the copper is not a choice for us because it gets oxidized really easily. So when we're talking about an outdoor horn antenna, the copper will be destroyed after 2 or 3 years, or I don't know, with rain or snow even in much less in a few months. Gold is really expensive. It was out of the choice because it is really expensive, especially for a horn antenna which is that big. So we ended up to nickel. Nickel coating is a quite average solution, but it's not disturbed that much from the weather conditions, and it's not that expensive like gold. So that's why we went for the nickel. Yeah.
You mentioned that the receiver will be on the back of the feeder so that you eliminate the need for extra cables and stuff like that. But how will it be weatherproofed? And I think that from the range, also from high and low temperatures for the receiver to work correctly. How is this supposed to be?
There's going to be a feed box. Stefan, so I think you have already the feed box from your end.
No, we don't have the box, but the size of this board, the Argos board, is about 50 centimeters, no, even less. So a special casing will be built where everything will be inside, along with the RF board that goes in front of the RF sock. And it will be weatherproofed and directly attached to the horn.
Does it also need the temperature control?
That's a good question. So the RF sock board and the RF sock chipset actually gets a little bit warm. So it has active cooling. It has a small fan over the chipset. But we think that we could go away with passive cooling if the case is made out of metal, the casing where the RF sock would be encased. And then maybe we could go with passive cooling and keep dissipation to the air.
I'm not concerned not with the board itself, but with high temperature in the summer, because it would be exposed to the sun, and low temperatures in the winter. If it's going to cause some damage that will wear down the boards faster, probably.
Yeah.
The release.
So if is painted white outside. During summer, we can calculate everything, I believe, but we can also do some testing. The problem will, I don't know, I can't answer for sure, but these are things to consider. We have not considered them yet so much. So how much the external temperature or the sun radiation will affect the temperature.
And if there is a closed box, so it can easily get like 67 degrees Celsius during the summer if the sun hits it. Like,
Depends on the material, on the color, depends on many things. But you can also have some external things to help with the heat dissipation.
and fans for this.
Or yes, we can have forced-air circulation, but then it gets a little bit tricky to make it weatherproof. It has active cooling. But we could use active cooling with some water-cooled system, a closed-loop water-cooled system. But this will increase the weight, and then we have to go back to how the
feed arms.
the feed arms will be. And it's something that we have not yet considered or thought very
It
carefully.
would also be mounted under the antenna, but you need some cables.
Then we will have cable losses. So
Yeah.
it's
We definitely want to avoid that. This is, yeah, we don't really want cables at all, let's say.
That makes sense.
Yeah. I think there was also another question.
Yeah, if we have time.
Yeah, sure. I think we do have plenty of time. So
Regarding the reflector system that you simulated, was that the 0.38 configuration?
Sorry?
The reflector system that you simulated, CST, was that
0.38, yeah. This is the F over D, 6 meters diameter. The only, yeah, of course, it was, let's say, we didn't apply any surface roughness, which is not, let's say, the ideal case. So far in our simulations, it's just a perfect surface for the reflector with no roughness. Because if we apply roughness, like 1, 2, 3 millimeter, let's say, roughness at the surface of the reflector, then this is going to be a huge problem for us in CST, in the electromagnetic solver with the number of the cells. Yeah. Generally, the structure is that huge that we cannot really simulate it like in brute force. This is how we say it, the antenna engineers, like just put the dish and the horn antenna and just simulate it. That's why we're using this special method, this SAM method for the dish, the system assembly modeling, because this method it gives you the opportunity to simulate the feeder with the time domain solver, which is better for the feeder. Simulate the huge structure of the disk with an integral solver, which is better for the number of the cells and the time consuming, let's say. And then this SAM procedure of CST converges the two solvers and gives you realistic results. But so far, we cannot really do it like a time domain solver for everything. This needs like billions of cells, and you need maybe 50 PCs running all together. Yeah.
And also the reason I'm asking is I noticed that your 10 dB, 10, 12 dB beamwidth of your field is around 90 degrees with ED 120. So my question is, are you still considering bigger Frontend to design it differently? Because I assume your aperture efficiency is, I mean, you showed the spillover efficiency, but I wonder what your aperture efficiency is in this case. You need 120.
Okay, sorry, you said 9 degrees.
10 dB or your field is around 90 degrees.
Okay, but this was in which field? Maybe show that in that field, or
It was the second one.
Okay.
So about maybe 100 degrees at 1 gigahertz, but as you go to higher frequencies, then your beamwidth narrows quite a lot.
Yeah, yeah. Yeah, that's the case. I mean, if it's possible, repeat the question so everybody from online can listen to the questions as well. Ah, okay. Okay. Okay, so the question was actually that at the higher frequencies, the taper angle is not 120, it's much less. So if we're considering maybe for a different f over d ratio, the problem with the f over d ratio is this. Even if we go with a megatron solution, we would like also to have a reference, let's say. We would like to buy also an off-the-shelf reflector and have a reference, you know, just like a prototype. And it's quite, I think it's impossible to find something very different from 0.38 or 0.40 for an off-the-shelf reflector. You have to go for a custom-made solution. And then you have a problem with the cost, because if you imagine that we're talking about an off-the-shelf reflector costs something like $10,000 or $15,000 for a fixed f over d ratio. If you go to the company and say, okay, I don't want 0.38, I want 0.19, it's going to be 3 times the price, because it's going to be custom made. So it's a quite big problem now, because we don't have many options, let's say. Megatron is a really good option because they can do a custom made solution, but then we will not be able to compare it with a ready, you know, an off-the-shelf selection. So it's a bit tricky.
No, I can appreciate that, especially
Yeah.
120 degree of something that angles challenge the one band. So I'm just asking what your options are. And the other question maybe on this you can answer as well. I see that if you look at the reflector system, the half-hour beamwidth of the reflector system is below 3 degrees. I don't know.
Sorry, the
half-hour beamwidth of your reflector is below 3 degrees.
Below 3 degrees.
The other, just look at the beamwidth at 3 degrees. I don't know, for your field of view of 10 square degrees, what should half-hour beamwidth be? Is, I don't know, are you achieving the 10 square degrees with this 6 meter reflector?
This is, and correct me, John, if I'm, I think this is the classic trade-off with this type of project. You want really high gain for the sensitivity, let's say. So you need the really the narrow field, let's say. But then for the field of view, you have the problem. Yeah, it's
I understand
for us. It depends actually from let's say the astrophysicists what they prefer to where to focus. Let's say if we want to focus more in the field of view, or we want to focus more in the sensitivity from let's say.
Yeah, it's clearly still a work in progress.
Yeah, I was just wondering what's the driving requirement for this, the field of view, then, yeah, but that was just, I don't expect the answers.
So there are 2 more questions from Jens and Johan.
Yeah, so there are 2 hands raised online. So I think you can. Do you have a comment or a question?
So a very quick question, hopefully. Given, I mean, this is preempting a talk which is going to come later. But given that you now have the data from the sites for the RFI testing, do you also envisage that we're going to need notch filters as well as bandpass filters in the front end chain?
Probably. I'm sure that Thanasis tomorrow is going to give a presentation, a detailed presentation about the RFI measurements. We'll discuss this better, can talk about this. But from the results that we have seen so far, I think we're going to have some notch filters for sure.
At the lower end of the band, I guess.
Yeah, especially at the lower end of the band. I mean, there are like some specific frequency ranges, 4 or 5 through 1 to 3 gigahertz. There are some specific 3, 4 different small sub ranges that they are always, of course, occupied mobile, telecom occupation. And we definitely have to think about something to deal with them. I mean, from a filter point of view.
Okay, so Yannis, you can.
Yeah, my question is about, I hope I didn't miss anything because it's difficult to hear from the people in the room. So it's about the surface accuracy of the antennas. So I understand it's not a very important parameter for these low frequencies. I think you mentioned order of 0.9 centimeters at some point, but are there prospects to go to higher frequencies, which will open also other scientific windows for Argos? And should this be taken into account for maybe a solid surface antenna or take care of the accuracy? What do you think?
Yeah, the 0.9 is not actually the surface roughness. It's the mesh gap. If you have a mesh reflector, the gap between the mesh lines, let's say. Ideally, of course, yeah, we prefer the solid solution, and this is another also advantage provided by Megatron, because Megatron is the only company from the 3 that I presented that they have a solid reflector solution. Ideally, of course, we prefer the solid because it's then we are open, as you said, to experiment and to do more things, of course. Vassilis, do you want to also add something?
Actually, the other companies had some solid surveys as well, but it was really, really expensive. So that's why they were out. And yeah, actually, in discussion with the companies, we said that we are interested for a bandwidth from 1 to 3 gigahertz. So they provided this kind of solution. So I believe, I don't think I can get much higher than that.
Okay. And one other short question, in one of the last beam patterns that you showed around 2 and 3 gigahertz, I think there are some high first side lobes. Is this something that can be mitigated somehow?
Yeah, this is something that we got. I think you're talking about the parabolic dish reflector.
Yeah, this
one. Yeah, this is something that we have to take into consideration. It's something that we didn't expect. This is quite a recent result that we got. Yeah, for sure, we have to do some adjustments and try to eliminate this. It's around it's around minus 23, 24 dBs. It's not that.
It's not too bad, but yeah, but.
Yeah, it's not too bad. It's something that, it needs some consideration for sure. Of course, for the lower frequencies, it's much better. Here we are at minus 30, 35, yeah. So that's not a problem. From minus 13, below minus 30, I think it's okay. So minus 35 is fine. But here, yeah, minus 23, it's quite tricky.
Indeed. Yeah, okay. Thanks.
Okay, any final question for Leonidas? So I think if not, we can conclude the session.